We now moved on to our next unit, which is mathematics as a tool for geometric designs. So for our learning outcomes, that would be applying geometric concepts, especially isometries, in describing and creating designs, and contributed to the enrichment of the Filipino culture and arts using concepts in geometry. So let's define geometry, geometric design. So it's a branch of geometry that focuses with the construction and representation of free form. Fractal geometry, on the other hand, it's a new geometry which describes the many forms that arise in nature. So it's very specific. This is applications of what can be found in nature. Fractals are objects that continually reveal new features at smaller scales, such as coastlines. So if you're going to look at it, you can see some patterns, corals, and mountain ranges. So if you are going to look the smaller part, it would look like the bigger part. So parang the zoom in, when you zoom in and you zoom out, you can actually see the bigger picture of what you can see when it is in smaller form. So self-similar fractals, these are fractals that look similar to itself when examined in different scales. So when you looked at the presentation here, look in the bigger picture, and when you go at a smaller scale, you can actually see the bigger one, how it look like as a whole. So that's self-similar fractals. Contour set, on the other hand, it's a fractal generated from a line segment. So if you can see, you have a line segment here where the middle um, third of each line segment is deleted. So this is the third, 1/3 of it is deleted until eventually the line turns to dust. So actually, if this will continue, then you will see the smaller portion, which we can no longer see the smaller version because it's already very tiny as dust. Okay, this one is Sierpinski triangle that is produced by starting with a solid block equilateral. So you will have this is an equilateral triangle. When you say equilateral, you all the sides are equal. And iterating with the following rule: for each block triangle in the current figure, connect the midpoints of the sides and remove the resulting inner. So if you're going to locate, this is already our midpoint, and then we connected it with our um, with a line, and then we now have 4 smaller equilateral triangle, but we will not be putting anything in the middle. So for the smaller triangles, we now uh, look for the midpoint, and again we do the same thing with each of the uh, given or identified midpoints of the smaller uh, equilateral triangle, and then until you can create, you do it into a smaller version. Well, the Sierpinski sponge, it is using cubes. Sierpinski triangle is using triangles. For the sponge, it's using cube. So iterating within the rules. So this one is 2D. You have the bigger cube, and then the current object. Divide each cube of the current object into 27 identical subcubes and remove the central subcube and the center of each cube. So it's very difficult to be creating or showing it here, but more or less this is how the output would look like. For Barnsley fern, it's a fractal produced by random iteration. It looks like very much like a real fern. So if we are going to look at this part here, it is actually it looks like the bigger part, and you have here the smaller part. It looks like the bigger part. So that's Barnsley fern. Symmetry, it is a property of an object that remains unchanged and under certain conditions. So we have reflection symmetry. This is when an object is mirrored in a straight line and it appears unchanged. So if you're going to get the half of it, katunga, it's just a reflection of the other side. Or if we get the vertical half, it's just the same as the other half. So it mirrors itself. That is the reflection symmetry. For rotation symmetry, if you're going to rotate the object at a certain angle around a point, it remains unchanged. So for example, this star, if you move from this, if you move this one and move it here, uh, the object still looks the same. It doesn't change. So that's rotation symmetry. Translation symmetry, when a pattern is moved to the left or to the right, it stays the same. So translation, moving left or right. Tessellation, on the other hand, it is a way of making patterns into a two-dimensional plane. These patterns are structured in such a way that there are no gaps or spaces, and the pattern is identical to each vertex. It is also considered a form of art called tilings. So it is applied in tiles and other art forms, which we can discuss later in the second part of the video. So for regular tessellation, it is a pattern made by repeating a regular polygon. So when you say regular polygon, you have all sides are equal, or it forms, it connects, because when you say there are irregular polygons, it would mean that the sizes are not the same. So the main characteristic of a regular polygon is that the polygons have the same measures in all sides. So in this case, for the triangles, they are equilateral. And also for our four-sided polygon, we have a square. So basically in this tessellation, we only made use of squares and equilateral triangle. So this is one type of tessellation. The second type of tessellation, it has a pattern that made up of two or more regular polygons. So in this case, we have the triangle, we have the square, and we also have the hexagon. So the main characteristic is that the patterns at each vertex are identical. So if you're going to look at this part here of our pattern, it looks the same with this pattern. That's semi-regular tessellation. Translation tessellation, it is a shape that is easily slid over the paper and redrawn in a piece in a different place. So looking at this, we have this one, and then the cut part here is moved on this side, and we cut this part here and placed it here. So this will be our resulting figure. And then we can now create our tessellation using the given figure. Rotation tessellation, the pattern is rotated by, of course, rotating it at around a point. So a rotation, also known as switch, happens when an object is rotated in circular motion. So we have this pattern around a fixed central point. So I think there was a time, not very sure, if you were able to have that particular material wherein it was sold in the market, and then you just play with it, and then you can form this particular figure. Okay, for now, that would be all. If you have some questions and clarifications with any part of the video discussion, kindly write your questions in the comment section below, not in the YouTube, but in our group page. Thank you so much.